So in section 5.3, we're just solving various logarithmic and exponential equations using what we know. Okay. All right. So the first one we have is 4 times e to the 2x is equal to 5. What is the value of x that makes the left-hand side equal to 5? And this is where you got to know the properties of logarithms. Okay. Now I got to remember what I did with my chalk. I know it's around here somewhere. All right, so we have 4 times e to the 2x is equal to 5. So we got to isolate x on the left-hand side, right? Let's solve for x. Well, whenever the variable you're solving for is an exponent, you know you're going to need a logarithm. Okay. So the first step is, this is 4 times e to the 2x. So we can isolate e to the 2x on the left-hand side by dividing both sides by 4. So we have 4 times e to the 2x divided by 4 is equal to 5/4. 4's cancel, okay? And we're left with e to the 2x is equal to 5/4. Okay? Now, one of the properties of the natural log function from section 5.2 is the natural log of e to the x is just x, right? So we got 2x in our exponent. So we can write that property as the natural log of e to the z power is just equal to z. Okay? Z is just a dummy variable. Okay? Just like x is a dummy variable here. Okay? So if the left-hand side is equal to the right-hand side, I can make these two quantities arguments inside the natural log function. Okay, so you know how when we solve x squared, so we have x squared is equal to 9. Okay, so we'll take the square root of both sides, right? Well, similarly, we can take the natural log of both sides. Okay, and make these two quantities arguments inside the natural log function. So we have the natural log of e to the 2x is equal to the natural log of 5/4. Okay? So taking the natural log of both sides is analogous to taking the square root of two sides of an equation. Okay? Well, now by this property of the natural log function, my z in this case is equal to 2x, right? So the natural log undoes the natural exponential function, and we're left with 2x on the left. And on the right, we have the natural log of 5/4. Now this is a real number on a real number line, right? There's no variables inside here, right? So if you have a calculator and you type in the natural log of 5/4, right, and hit enter, you'll get a decimal value. Okay, it's a real number on a real number line. And now we can divide or multiply both sides by 1/2, divide both sides by 2, or multiply both sides by 1/2. 1/2 times 2, right, is 1. And so we're left with x is equal to 1/2 times the natural log 5/4. And so you can leave your answer just like that, right? If you want to. In fact, I think we will. You could also apply the quotient rule to the natural log of 5/4 if you wanted to, but it's not necessary. Yeah.
Are we going to be given the properties on like any exams to remember this?
Yeah. In the math department, College of Charleston, no formula sheets, no calculators, no formula sheets. Yeah, it's all up here. Yes, ma'am.
5.3 is going to be on the testing next week.
Yeah. It's only Thursday. You're taking the test Wednesday. It's 6 days of what? Yeah, it'll definitely be on there. Okay. All right. Any questions on that, ladies and gentlemen? All right, in B, we have 2x is equal to 10. Now we're going to show 2 equivalent solutions to this problem. Now this is really basic. 2x to the x is equal to 10. The variable x is an exponent, right? So it's going to involve a logarithm, right? So this is an exponential statement. Previous section, you had to go from an exponential statement to a logarithmic statement, right? What's the logarithmic statement?
Log a of x equals y.
So back in 5.2, right, we said if x is equal to 2 to the y, or x is equal to a to the y, then y is equal to log base a of x, right? Those are equivalent equations. If one's true, the other's true. Well, x is now the x as we've taken the place of y, okay? So what's x equal to?
Log base 2 of 10 equals x.
Yeah, log base 2 of 10. That's the corresponding logarithmic statement. That's the answer. Now, that's a real number on the real number line, log base 2 of 10. So modern calculators today, you can do logarithms in any base, right? You can TIs, right? You can type in log base 2 of 10 and it'll spit out the decimal value. Back in the olden days, when I was an undergrad, we only had 2 logarithmic functions on our calculators. We had the natural log function, ln, and then we had the common logarithm, log base 10. So in order to solve this equation, you had to either use ln or log base 10. Okay, so I'm going to show you the alternative way of getting the solution. And the answer is equivalent to log base 2 of 10. We start off with 2 to the x is equal to 10. And like we did over here, we can take the natural log of both sides, right? Because the left-hand side equals the right-hand side. And so we have the natural log of 2 to the x is equal to the natural log of 10. Natural log of 10 is a real number, okay? On the real number line. Well, by the property of the natural log function, you know that the natural log of 2 to the x, or, excuse me, that's coming out wrong. By the power rule, from the laws of logarithms, right? By the power rule, the log of 2 to the x, the log of m to the c power, I can bring that exponent c down in front of the logarithm, right? And that's equal to c times the natural log of m. So, instead of putting parentheses around it, I can just write it natural log of 2 to the x to be consistent with what I have typed here, okay? So my m in this case is 2, and my c is x, so I can bring the x down from the natural log. And I have x times the natural log of 2 is equal to the natural log of 10. Okay? So that is using the power rule of logarithms in section 5.2. And now you can see this is a product, okay? And so natural log of 2 is a real number on the real number line. It's like equal to 0.69 something. So I can divide both sides by the natural log of 2 and isolate the x on the left-hand side. So x times the natural log of 2 divided by the natural log of 2 is equal to natural log of 10 divided by the natural log of 2. Element of 2 cancels on the left in the numerator and denominator, and I'm left with x is equal to the natural log of 10 divided by the natural log of 2. This looks like two different answers, doesn't it? But it's not. They're equal. Log base 2 of 10 and the natural log of 10 divided by the natural log of 2 have the same decimal value. Okay? And so that leads us to what is called the change of base formula. Log base A of m, okay? So over here, right, my A is 2, my m is 10. That is equivalent to the natural log of m divided by the natural log of A, okay? So A is the base, right? M is the argument. So this is equal to the natural log of the argument divided by the natural log of the base. Okay? That is called the change of base formula. Okay? And you can see when you put 2 in for A and 10 in for M, we end up with this over here. Okay? So back in the olden days, okay, that is how we had to solve a problem like this, right? If we had to give it a decimal answer, we had to use the natural log function. Okay. All right, any questions on that, ladies and gentlemen? All right. In C, we have 2 to the x is equal to 7 raised to the 3 plus x power. Now back in section 5.1, right, and you had a quiz on this yesterday, we learned about the one-to-one property of exponentials, right? And this is an exponential on the left is equal to an exponential on the right. X is in the exponents, okay? And if the bases of the two exponentials are the same, you can equate the exponents, right? But we cannot, 2 and 7 cannot be rewritten with a common base. So we gotta do something different, right? We can't use that one-to-one property. So we're gonna do what we did over here. Use the natural log function, okay? Now you could use any log and any base, okay? But the natural log function and the natural exponential function are the two functions that get used 99.9% of the time in the sciences and mathematics. Okay? So that's why we stick with it. So the left-hand side is equal to the right-hand side. And so I can make these two guys arguments inside the natural log function. So I take the natural log of the left-hand side. That has to equal the natural log of the right-hand side, okay? So they're sort of like a one-to-one property with logarithms, okay? Just like there's a one-to-one property with exponentials, okay? Well, now you know from the power rule that we just used, this x, right, that's an exponent on the number 2, right, can be brought outside the natural log. And we have x times the natural log of 2 on the left. And now this exponent 3 plus x on the number 7 can be brought out in front of the log. And we have 3 plus x times the natural log of 7. Okay? So that's the application of the power rule of logarithms. Put it back up just to remind you, okay? So this exponential equals this exponential, so I can make them arguments inside the natural log function. Okay? And take the natural log of both sides. And then I apply the power rule. Now, the natural log of 2 and the natural log of 7, those are real numbers on the real number line. Just like plus 2 and plus 7 are real numbers on the real number line. So we treat the natural log of 2 and we treat the natural log of 7 just like we would the numbers 2 and 7. Okay? Now, what I'm going to do is I'm going to distribute the natural log of 7 inside parentheses here. Okay? So if all I had was, if I had 3 plus x times 7, right? You know how to distribute plus 7 inside the parentheses, right? Well, we're going to do the same thing over here, but instead of distributing plus 7, we're distributing the natural log of 7. Okay? So we're going to distribute this guy inside the parentheses. And so we have x times the natural log of 2 is equal to 3 times the natural log of 7 plus x times the natural log of 7. Okay. And if this was just plus 7 out here, right, we'd probably write that as 7x. But I often put that, when I'm working with natural logs, put it after the x, just for clarification purposes. Because I don't want the x to end up inside the argument of the natural log function. Okay. And now this technically is a linear equation. If this was x times 2 is equal to 3 times 7 plus x times 7, you'd solve that in 30 seconds. Okay, solve for x. We're going to do the same thing. Okay. So we're going to put all the terms with x in it on the left-hand side. right? And then factor out the x. So I can move x times the natural log of 7 to the left-hand side by a subtraction, right? And when I do that, I have x times the natural log of 2 minus x times the natural log of 7 is equal to 3 times the natural log of 7. All I did was subtract x times the natural log of 7 from both sides. Well, now on the left, we have a difference of two terms. X is a common factor, so I can factor out an x. And so I have x times the natural log of 2 minus the natural log of 7 is equal to 3 times the natural log of 7. So again, ln of 2 and ln of 7 are real numbers, and so the difference is a real number. And now to isolate x on the left, I just divide both sides by what's inside parentheses, right? Ln of 2 minus ln of 7. And I have x is equal to 3 times the natural log of 7 over the natural log of 2 minus the natural log of 7. That is the exact value of x that makes the left-hand side equal to the right-hand side in our original equation. Cool beans? Okay. So this stuff, you know, it's different from what we've been doing, what you've done in the past, but it's not, once you understand it, it's really not that mysterious at all. Okay. All right. In D, we have two times the natural log of 3x is equal to 4. So now, instead of x being in an exponent, it's part of the argument into the natural log function, right? And we still got to isolate the x, right, to solve for it. Well, first we're going to isolate the natural log of 3x by dividing both sides by 2, right, because 2 is a factor. So we have 2 times the natural log of 3x over 2 is equal to 4 over 2. 2's cancel on the left, and we're left with the natural log of 3x is equal to 2. So now we have the natural log of 3x is equal to 2. So now we got to isolate the 3x, right? Get rid of the ln. How do we get rid of the ln? What's the inverse? What's the inverse of the natural log function?
It's like ln e to the square.
What's the inverse of the natural log function? The natural exponential function, right? So we're going to use e, okay? So let's remind ourselves of this property of the natural log function from 5.2. If I have e raised to the natural log of z, what's that equal to?
Z.
Just z, right? So this is from 5.2, bottom page 3, okay? e raised to the natural log of x is just x, right? The argument going into the natural log function. So instead of x, I use z as my dummy variable. So e raised to the natural log of z is just equal to the argument going into the natural log, z. Okay. So left-hand side equals right-hand side. So I can make the left-hand side and the right-hand side exponents on the number e, right? Remember the one-to-one property of exponentials? Okay. So I have e raised to the natural log of 3x is equal to e squared, right? Exponential on the left equals the exponential on the right. So the exponents must be equal. Or let me rephrase that. So the base of the exponential on the left is equal to the base of the exponential on the right. So the exponents must be equal. Log of 3x is equal to 2. Okay. So I didn't change the value of anything.
How do you know to use that property instead of the one above it, the natural log that is under the x?
Well, we don't have e to the x in here.
Okay.
We have 3x. Yeah. Okay. And that comes with practice, right? I mean, it's like hitting golf balls. You hit a million golf balls, right? You end up knowing how to hit golf balls after you hit a million. Okay. I've solved 1,000 equations like this. So practice makes perfect. Okay. All right. So this property of the natural log function says e raised to the natural log of 3x is just equal to 3x. So we have 3x on the left is equal to e squared on the right. Is e squared a real number?
Yeah.
You know, remember what's e equal to? Remember? 2.718. Yeah, 2.718. So this is like 2.718 squared. Okay. So this is a real number on the real number line on the right hand side. Okay. And now you know to solve for x, all you gotta do is divide by 3. And so we have x is equal to e squared over 3. So e squared divided by 3 is the exact value of x that makes the left-hand side here equal to 4. Okay. Any questions on that, ladies and gentlemen? Yes, sir.
So, in like the like third to last step, does the natural log cancel out the e, and that's how you kind of like get the 3x equals?
Yeah, they undo, right? They're inverse functions of each other. So that's why the e and the ln go away, and you're left with z, right? They're inverse functions of each other.
Thank
you. Yep. It's kind of like how, you know how square root undoes squaring?
Yeah.
So e and ln are like square root and squaring. They undo each other. Okay. All right. So now we're going to solve another type of logarithmic equation. And we'll be using the product rule of logarithms, solving these. So we have log base 2 of x plus log base 2 of x plus 4 is equal to 5. So we gotta find the value or values of x and make the left-hand side equal to 5. Okay? Now, in 5.2, I think the last thing we did yesterday was condense a logarithmic expression, right? We went from 3 logs down to 1 log, okay? And so we're gonna do something similar with log base 2. We're gonna go from 2 logs on the left to 1 log on the left, right? That's called condensing. And we're gonna use the laws of logarithms to do that. We're actually gonna use the product rule. Okay. And the product rule says, so we'll use this side of the table, okay? Because our base is 2. And one thing you gotta recognize, the bases are the same, right? These rules don't apply if the bases are different. So going from right to left, the log of m plus the log of n is equal to the log of m times n, right? That's the product rule. So we're gonna go from a sum to 1 log, okay? So our m in this case is x, and our n in this case is x plus 4, and our base a is 2. So by the product rule, this is equal to log base 2 of x times x plus 4. Now I'm going to put that in, I'm not going to use nested parentheses. I'm going to use brackets instead, okay? Remember, when you use nested parentheses, you got to have the same number of left-hand parentheses as right-hand, right? And so it's just kind of easier to use brackets instead of another set of parentheses. That is equal to 5, right? By the product rule, of logarithms. Are you with me? All right, now, this is a logarithmic statement, right? You got just 1 log on the left is equal to a number on the right. It has an equivalent exponential statement, right? This from page 1 of 5.2, right? Do you remember what the 2 equations are? So log base, if y is equal to log base a of x, then x is equal to a to the y power, right? Well, a is equal to 2, y is equal to 5. Now what's different is the argument isn't just x, it's x times x plus 4. So we just replace x with x plus 4, or x times x plus 4. And so we have x times x plus 4 on the left, that's our argument, is equal to the base 2 raised to the 5th power. That is the corresponding exponential statement. Do we know how to solve for x? This is shaping up to be a quadratic equation. We know how to solve it. We solved 1,000 of those this semester. So you distribute the x, and you have x squared plus 4x, and 2 to the 5th, using your calculator or your fingers or whatever, 2 to the 5th is equal to 32. Well, now to solve that quadratic, right, we gotta get 0 on the right-hand side. So we subtract 32 from both sides. And now we can factor. This actually factors in, now you could use a quadratic formula, right? If you're having difficulty factoring. But this factors into x plus 8 times x minus 4 by the zero product property. X plus 8 has to equal 0, or x minus 4 has to equal 0. So x equals minus 8 and x equals 4 are the two solutions, right, to our quadratic equation. Either over here or over here. Okay. Here's the problem. It appears there are two solutions to our original equation. Minus 8 and plus 4. But one of those is actually a bogus solution. Which one is it? Negative 8. And instead of calling it a bogus solution, we call it an extraneous solution. Okay. Why is that? Remember, you can't take the log of 0, and you can't take the log of a negative number. So when you plug negative 8 in for x up here, you get log base 2 of negative 8. And log base 2 of negative 8 is undefined. If you put 4 in for x, the left-hand side, you can show the left-hand side does equal 5. Okay? Because you're taking log base 2 of 4 plus log base 2 of 8. And you can show that that does indeed equal 5. Okay? So you always have to check for extraneous solutions. Where did that extraneous solution come from? When we condensed. When we used the product property and went from 2 logarithms to 1, we created this quadratic, which has 2 solutions. Okay? And so, whenever you condense and you create a quadratic, you gotta look for that extraneous solution. Okay? All right. So we only got 7 minutes left. So there are 2 more on this page, but I think we'll save them for first thing tomorrow. Okay, in a regular class.